The Master's Research Program was carried out at the South Australian Institute of Technology in the School of Mechanical Engineering at the Levels campus. It consisted of the design, construction and testing of a differential stroke or Atkinson cycle engine. The prototype was constructed from a disused 90-degree V8 motor having the major portion of the centre removed. The head was re-welded, as can be seen here, and the rear portion of the motor was mechanically reconnected to reform the water and oil passages necessary for the operation of the new engine. Only one of the cylinders was used in the prototype. This particular cylinder was aligned vertically, leaving the unused cylinder on the side in a horizontal direction. The engine was re-sleeved and the clearance volume of the engine was reduced by means of metal added to the top of the piston and modifications to the combustion chamber within the head. The engine has an intake volume of 181 cubic centimetres and an expansion volume of 543 cubic centimetres and a nominal compression ratio of 7:1. The original distributor has been retained. This view shows the flywheel end of the motor. The engine is connected to the dynamometer through a counterbalance weight with angular graduations on the rim read against a timing marker. The coupling is bolted onto the original harmonic balancer. Front covers enclose the timing chain and sprockets. To accommodate the extended motion of the piston, the crankshaft has been lowered along the cylinder centre line by means of a steel spacer block. The timing chain has been extended. Removal of the front covers and sump allows a complete view of the epicyclic gearing, crankshaft, oil pump and timing chain systems. The timing chain tension is adjusted by means of an idler sprocket mounted into an eccentric boss, which can be rotated and held in position by a locking plate. The camshaft is disassembled in a conventional manner and can be easily removed. The camshaft has been reduced in length to suit the block. The oil pump has been spaced down by means of an insert to clear the crankshaft assembly. It's held in place by 4 long studs inserted into the block. The differential stroke of the piston is achieved by attaching the connecting rods to the epicyclic gearing system. Seen here are the ring gear, the planet gear and the eccentric, upon which is attached the big end of the connecting rod. The connecting rod is basically of steel construction with a white metal bearing finish. The eccentric is made up of a steel section and an aluminium section held together by bolts. The crankshaft is held in position by 2 main bearings. Shown here is the front bearing cap being removed. The second bolt is anchored into the main engine block. The front bearing provides only radial support. The rear bearing is of similar construction but acts also as a thrust bearing to take any axial load. It's held in place by 2 long bolts screwed into the original engine block. The rear bearing can also be easily removed, showing the thrust face and the bronze journal bearing. The crankshaft is a two-piece construction bolted together from the rear. It can be taken apart by removing the retaining bolts and using an extractor. Relative angular movement between the two sections of the crankshaft is prevented by means of concentric and eccentric mating sections. The crankshaft assembly can be removed from the block along with the front bearing support. Removal of the wrist pin allows the connecting rod and piston to come out. The ring gear assembly and main bearing support also come away from the block. The modifications carried out on the block can be seen here, together with aluminium filling, which had to be poured into parts of the original engine to protect the oil from impurities such as rust. The rear section of the block is seen here bolted in position. Slotted holes allow rotation of the ring gear and corresponding change to the top dead center positions of the piston, affecting the compression ratio of the engine. Dismantling the eccentric is achieved by removing the two retaining bolts. Holes are drilled in the webs for balancing purposes, as are the holes in the planet gear. The lower portion of the eccentric is held by two Allen head bolts. Once the eccentric is removed, the ring gear can be pushed off. Three circumferentially disposed keys prevent the gear from slipping on its carrier. The carrier is also of steel and aluminium construction and can be split about its center. The gear can then be slipped from the crankshaft. The camshaft has been reconstructed from the original. The distributor drive is removable, as are the camshaft bearings and cam lobes. Spacers are inserted between the components and the cam lobes are held in position by a key and keyway arrangement. The full complement of parts required for the engine can be seen here. The testing of the engine was carried out on a Ricardo electric dynamometer capable of starting the engine and being reversed to act as a dynamometer. Engine speed was measured using a handheld digital tachometer. Particular attention has been taken to eliminate errors in the measurements due to stiction in the system. A simple carburettor with a variable main jet was used to adjust the engine for maximum torque conditions. The mass flow rate of fuel was indirectly determined from measurement of the volume flow rate and the physical properties of the fuel. Using a pressure transducer especially fitted to the spark plug and Tektronix engine analyzing equipment, pressure versus crankshaft diagrams could be obtained. From a magnetic pickup which responded to slots cut in the flywheel of the motor, pulses corresponding to the piston bottom dead center at the intake, top dead center of compression, bottom dead center of an equivalent Otto cycle, and the actual bottom dead center of the engine could be displayed on the photographs taken from the cathode ray oscilloscope screen. The pressure crank angle photographs were transformed into pressure volume diagrams either manually or by a computer digitizing program. The more complete expansion of the combustion gases within the cylinder was evident when the exhaust pipe was removed. In all, the prototype has completed over 400 hours of successful running on the dynamometer, allowing a remarkable insight into the actual thermodynamic operation of the Atkinson cycle engine.